This innocent-looking piece of Rust code is about to completely ruin our day, and lead us down to some of the most difficult parts of Rust that would make most people rage quit the language. Now let me set the scene. Imagine that you're building a backend service in Rust, and you have this user service interface, with a simple getUser method. Now how do you actually use this interface? Let's say you want to write a function, and this function accepts any type that implements user service. The question is, what should the type of this function argument be? If you've read the Rust book, you know there are two ways to do polymorphism in Rust. The first way is to use generics with trait bounds. Here, T is a generic that can be any concrete type as long as it implements the user service trait. Generics use what's known as static dispatch. This means at compile time, Rust looks at every place user service is called and generates a specialized function for each concrete type used. This approach doesn't add any runtime overhead. So this works great if we know exactly which implementation we're using at compile time. But what if we don't? What if the concrete type implementing user service isn't known until runtime? Well, in that case, we can use Rust's second way of doing polymorphism, dynamic dispatch. So let's go back to our original example that uses generics and static dispatch, and now switch to using dynamic dispatch instead via trait objects. Trait objects are defined using the din keyword, followed by some trait bounds. And in Rust, trait objects must always be behind some kind of pointer. In this case, the boxmar pointer. To understand why, here's a helpful diagram. The boxdin trait type actually contains two pointers. A data pointer pointing to the concrete value allocated on the heap, and a vtable pointer pointing to the virtual table that Rust uses to decide which method to call at runtime. The reason trait objects must always be behind a pointer is because Rust doesn't know the size of the concrete type until runtime, so it can only store a pointer to it. Okay, so going back to our code. We now have a trait which concrete types can implement, and a function that accepts any type which implements user service. We're done, right? Wrong. Without realizing it, we just opened up a can of worms that's going to lead us down into the very depths of some of Rust's most complicated features. So buckle up, grab a notepad, and let's begin our journey. This video is presented by the Rust Live Accelerator. More on that later. The first Rust error we see is this. The trait user service is not din compatible. What is din compatibility, you ask? Let's consult the Rust reference for guidance. A din compatible trait is simply a trait that Rust is able to turn into a trait object, meaning that it can be used behind din for dynamic dispatch. There's a long list of rules that traits have to follow to be din compatible, but we are only interested in one of the rules. A trait cannot have an async function, which has a hidden future type. This begs the question, why aren't async functions allowed, and where is the hidden future type? Let's look at our code again. In Rust, the async await syntax is simply syntactic sugar, just like in every other language that uses async await. If we desugar this method, it would look something like this. getUser is just a regular method that returns some type which implements the future trait. This Impl future return type is a special syntax in Rust called the Impl Trait syntax. But to understand why we need this special syntax here, we need to first take a quick detour into how async Rust actually works under the hood. So let's step away from traits for a moment and come back to this once we have a better understanding of async Rust. Let's look at the standalone async function to explain how the Rust compiler turns async code into state machines. Here, the Rust compiler sees an async function, but it doesn't execute it immediately. Instead, it rewrites the async function into a regular function that returns a compiler-generated state machine as the return type. Now remember, what async functions actually return is an Impl future, but for now let's think about the return type conceptually as an anonymous state machine. And let's call this state machine page content future. Conceptually, we can think of page content future as an enum, where each variant corresponds to a different state. There's a start state, a done state, and a number of states in between, corresponding to each time the function pauses execution because of the await syntax. Keep in mind that state machines can look different depending on the function body. For example, if we add more await points, the state machine can contain additional states. Because every state machine is different, Rust uses the future trait as a common interface. Each state machine implements the future trait, so runtimes like Tokyo can interact with any of them in the same way. To keep things simple, here's a highly simplified version of what that trait looks like. The key idea is the pull method. An async runtime like Tokyo repeatedly calls poll to let the future make progress. Each time poll is called, the future either returns pending if it still has work left to do, or returns ready once it can produce the final output. Futures deserve their own video, so let me know in the comments if you'd like a deeper dive. For now, this conceptual model is all we need. With that understanding of async functions and futures, we can end this detour and jump back to our user service trait. Remember, this async method doesn't really return an optional user. It returns a future, a compiler-generated state machine that will eventually produce an optional user. Now, here's the catch. That state machine can look very different depending on the method body of getUser, but we won't know what that method body looks like until a concrete type implements the trait. So now the compiler has a problem. How does it know what state machine to return? That's where the Impl Trait syntax comes in. In Rust, the Impl Trait syntax is one form of generics. Generics use static dispatch, so the concrete type of this Impl future will be determined at compile time and will be based on the concrete implementations of the getUser method. This brings us all the way back to our original error. The trait user service is not DIN compatible, and now I can explain why. Impl future is a type of generic, so it uses static dispatch instead of dynamic dispatch, making it not DIN compatible. That also makes our entire trait not DIN compatible as well. Async didn't break DIN compatibility. Hidden generics via the Impl Trait syntax did. So how do we fix this? By removing the generic return type from the getUser method. Instead of returning Impl future, we can return a trait object which uses dynamic dispatch. In this case, a boxed future. Now, every implementation of getUser returns the same pointer type, and the user service trait is now DIN compatible. The compiler error disappears, everything is good now. Until a second later when we try to compile our code again. This time we get a different error. The compiler tells us that DIN future cannot be unpinned, and at the bottom we see the trait unpin is not implemented for DIN future. The unpin trait relates to the concept of pinning in Rust. Pinning is a very important implementation detail of async Rust. It can also be hard to understand without context. So let's take another detour, this time to learn about pinning. At a high level, pinning is about one simple idea. Some values in Rust are not allowed to move in memory. Earlier, we saw that async functions are compiled into state machines, and those state machines live somewhere in memory. A state machine may store pointers to its own internal data, and that's a problem because if that state machine were allowed to move in memory, those internal pointers would suddenly point to the wrong place. That would be undefined behavior. Rust prevents this by requiring self-referential futures to be pinned, meaning once they're placed somewhere in memory, their location must not change. But how does Rust enforce this? In Rust, pinning is enforced through the pin smart pointer. The pin smart pointer guarantees that either the value behind the pointer will not be moved in memory, or it can be moved if it's explicitly safe to do so by implementing the unpin trait. Unpin is an auto trait, which means types in Rust implement the unpin trait automatically. However, in some cases, the compiler or you can explicitly decide not to implement the unpin trait if a type is not safe to move in memory. So how does this relate to async Rust? Now, most futures are safe to move in memory, so they implement the unpin trait by default. But some futures, especially ones that rely on references to their own internal data, need to stay in one place so that the references remain valid. For those futures, the compiler explicitly does not implement the unpin trait so that those futures remain at a fixed memory location. The key idea is that pin works for both types of futures. It provides a single, safe abstraction that Rust can use whether the future is safely movable or not. This system lets Rust support powerful async abstractions without giving up memory safety or performance. Okay, with that context of how pinning enforces that futures are memory safe, we can end this detour and jump back to the compiler error we saw earlier about the unpin trait. Now we're back to the user service. Again, the getUser method returns a future, more specifically a trait object, which can be any type that implements the future trait. Trait objects use dynamic dispatch, so we won't know the exact concrete type until runtime. That means the compiler doesn't know if this future implements the unpin trait, so it cannot assume that the future is safe to move in memory. Remember that futures are state machines. This future returned by getUser is the first state machine in our code so far. UseService is also an async function, so we can desugar it into a regular function that returns a future, which creates the second state machine in our code. Now, this is where the problem starts. The call to getUser on line 8 returns the first state machine. When we hit .await, the outer state machine 2, pauses execution and stores its state in memory so it can be resumed later. Because the state machine of a future is determined by its function body and its await points, this stored future includes the inner state machine. So if the second state machine is moved in memory, the first state machine moves with it. That's a problem because the first state machine is not safe to move in memory. So the second state machine, which contains it, is not safe to move in memory either. With this context, now we can understand why we were seeing the compiler error from before, which pointed out that the trait unpin is not implemented for the future returned from getUser, making it illegal for other futures to call await on it. To fix this, we need to give the compiler an explicit guarantee. We need to tell the compiler that getUser returns a future that is either safe to move, or that it will never move at all. And that's exactly what the pin smart pointer does. So instead of returning a boxed future, we can wrap it in a pin smart pointer. This tells the Rust compiler, please put this future on the heap, and pin it so it cannot be moved in cases where moving would be unsafe. Also, let's go ahead and remove these decorative comments. And revert the useService function back to using the async function syntax again. With the pin smart pointer in place, the compiler is satisfied, and our code compiles. So we can end our coding session knowing we understand Rust at a deeper level, right? Wrong. Our current implementation works, but only for our very narrow use case. Let's look at a couple of other use cases that break our implementation. First, let's take one small step toward a more realistic server. In practice, we wouldn't use the box smart pointer here because box implies single ownership. But what we probably want is shared ownership, because usually a user service is created once and shared across many requests and background tasks. That's exactly what the arc smart pointer is for. Arc stands for atomically reference counted. It's a smart pointer that lets us share the same service in a thread-safe way. Now that we have a shared service, it becomes natural to do more with it. For example, kicking off a background task that uses the service. If we're using the Tokyo async runtime, the standard way of doing that is by calling Tokyo spawn. So let's spawn a background task. And now we hit a compiler error. This error isn't about pinning anymore. It's about threads. When we call Tokyo spawn, we're giving Tokyo permission to run this task on any worker thread. That means anything inside the task might be moved to another thread. So the Rust compiler asks a new question. Is everything captured by this task safe to send to another thread? That's what the send trait represents. So what is the send trait? To find out, let's take another detour and talk about the send and sync traits in Rust. Before we go any further, let's pause and look at the actual definitions of send and sync in the standard library. Types in Rust implement send if it's safe to move ownership of a value from one thread to another. And types in Rust implement sync if it's safe for multiple threads to share references to the same value. Rust programs are often multi-threaded, and async runtimes like Tokyo often move tasks between threads. So Rust needs a way to know whether values in those tasks can be moved or shared safely across threads. That's exactly what send and sync are for. Send is about moving ownership, and sync is about sharing references. And both send and sync are auto traits. That means types in Rust implement them automatically by default. Only special cases opt out. With that mental model, let's go back to our user service code and revisit the send error we got and how sync will soon follow. Remember that we got this error. Future cannot be sent between threads safely. The compiler also gives us this helpful note. Service is a trait object behind an arc smart pointer, and this type does not implement send. Remember that the send trait is automatically implemented for most concrete types, but the compiler doesn't know the concrete type of a trait object until runtime. This means it doesn't know if the concrete type will automatically implement send, or explicitly opt out and not implement send. To fix this error, we can simply add a send constraint. This means the trait object has to be a type that implements both the user service trait and the send trait as well. By introducing this additional constraint, our original error is resolved. However, we get another similar error. Again at the top we see, future cannot be sent between threads safely, but this time for a different reason. The compiler tells us that the future returned from the getUser method does not implement send. So let's go back to the original user service trait and its getUser method. Again, this getUser method returns a trait object, which may or may not implement send. So just like before, we need to introduce a send constraint. Now, the return trait object must implement both the future trait and the send trait as well. Once again, the error is resolved. But the compiler is still not happy, and gives us another similar error. Just like before, at the top we see, future cannot be sent between threads safely. But this time, the compiler note isn't very helpful. The message says, service is a trait object that implements the user service and send traits, but this type is still not send for some reason. Luckily, another part of the error message is more helpful. It says sync is not implemented for din user service plus send. To understand what this means, we need to talk about arc. The arc smart pointer we're using here allows multiple threads to share references to the same underlying value. Remember that a type in Rust implements the sync trait if it's safe for multiple threads to share references to it, and arc needs to be thread safe, so it will require the underlying value it holds to implement the sync trait. But in this case, the underlying value is a trait object, so again, the compiler doesn't know its concrete type until runtime. And we don't know if this concrete type will automatically implement sync or explicitly opt out and not implement sync. To fix this error, we can add a sync constraint. Now this trait object becomes a type that implements the user service trait, the send trait, and the sync trait. By adding this new constraint, our error is resolved once again. But just kidding, no more errors. Our code is now compiling. However, notice that up until now, we haven't actually implemented our user service trait on any type. So let's explore what happens when we do implement it. Here is our user service trait so far. Let's reformat our code to make it slightly easier to read. Okay, now we'll define a DB user service struct and implement our user service trait. The function body looks like this. We create a new pinned box smart pointer which holds an async block. The move keyword tells the async block to take ownership of captured variables. In this case, the async block takes ownership of ID. Inside the async block, we create a new user instance and return it. Pretty straightforward, right? Unfortunately, the Rust compiler doesn't think so. It gives us the following error. Lifetime may not live long enough. Alas, we have just encountered one of the trickiest parts of Rust. Lifetimes. You know what that means, right? That's right, another detour. This time to understand what the heck lifetimes are and why we need them in Rust, especially in this particular context. Lifetimes in Rust are closely related to two other concepts, generics and references. Earlier in this video, we touched on generics. By defining the generic T, we can accept any type that implements a specific trait. This makes our function a lot more flexible than if we simply specified one concrete type like DBUserService. Now currently, this function takes its argument by value, but oftentimes we don't want to pass an argument by value. Instead, we want to accept a reference to that value. References are a special type of pointer. Unlike a raw pointer, references in Rust are guaranteed to always point to valid memory. In order to enforce this guarantee at compile time, the Rust compiler has to keep track of how long a reference is valid for. For example, if we define a reference inline when calling useService, the reference will be valid for the duration of that function call. But if we extract the reference out into a separate variable, that reference will be valid until the end of the main function. This means we can continue to call useService and pass in the same reference. The span of code that a reference is valid for is called the lifetime of that reference. So what does this have to do with generics? Well, if we look at our function signature in isolation, the compiler doesn't know the exact lifetime of the reference passed in. In fact, this function can be called with references that have a variety of lifetimes. This means our function signature needs to be generic over the lifetimes of any references passed in. And the way we specify this flexibility in Rust is by using generic lifetime annotations. Declaring a generic lifetime is similar to declaring a regular generic, except this starts with an apostrophe. In the Rust community, we call this a tick. The tick is followed by the name of the generic lifetime annotation. It can be as concise as a single letter, or more verbose and descriptive. This is actually the real definition of this function. However, in many cases, the Rust compiler can infer what the generic lifetime annotations should be, so we don't have to write them out manually. But in some cases, the compiler cannot infer the lifetime annotations, so we have to help it out. For example, let's define a new function called pickService. This time, the function accepts two arguments, dbService and cacheService, and returns one of them. If we try to compile this code, we would see the following error: missing lifetime specifier. And the hint at the bottom says, this function's return type contains a borrowed value, but the signature does not say whether it is borrowed from dbService or cacheService. Basically, the compiler is saying that it's unable to automatically determine the relationship between the lifetimes of the two references passed into the function and the lifetime of the reference returned from the function. So it's asking us to manually write out the generic lifetime annotations for this function signature. Let's give that a shot. The first approach we can explore is to define three separate generic lifetime annotations. We'll assign tick A to dbService, tick B to cacheService, and tick C to the returned reference. This is basically saying that these three references will have lifetimes that are completely unrelated to each other. But we know that cannot be true, because the value we return must be either dbService or cacheService. The output lifetime must be tied to the input somehow, so we need to define that relationship. One way we can define a relationship is by adding a where clause with lifetime bounds. This code is saying that the lifetime of A and B must both live at least as long as lifetime C. Or to say it another way, lifetime C is not allowed to outlive lifetime A or B. This makes sense because this function might return either input. Since we don't know which one ahead of time, the returned reference must be valid for both cases, so it cannot live longer than either input. Our code now compiles. That's pretty good, but it can be improved. We can specify the relationship between these three references in a simpler way. Remember that lifetime annotations are a form of generics, so we could define three separate generic lifetimes and use a where clause to describe the relationship between them. But in this case, we can simplify things by defining a single generic lifetime and applying it to all three references. By doing that, we're explicitly tying their lifetimes together. We're telling the Rust compiler that both input references are valid for at least tick A, and the reference we return is valid for that same tick A. The compiler will then choose a lifetime that works for both inputs, effectively the overlap between them. And just like before, that guarantees that the returned reference cannot outlive either input. With that relationship made explicit, the compiler is happy and our code still compiles. Before we end this detour, I want to talk about one more type of lifetime, a special case called the static lifetime. A reference with a static lifetime is valid for the entire duration of the program. A simple example is a string literal. A string literal lives directly inside the compiled binary, so any reference to it is guaranteed to be valid for as long as the program is running. That's why it has a static lifetime. In summary, a reference with a static lifetime simply means the data it points to is guaranteed to be valid for the entire program. With that in mind, let's end this detour and jump back to our user service implementation, which had a lifetime-related error. This is our implementation from before. We are trying to implement our user service trait and its getUser method. The implementation is pretty straightforward. We are simply returning a new user instance inside of an async block and wrapped around by the box and pin smart pointer. Note that the async block is a feature that captures the ID argument passed into the getUser method. Now, when we compiled this earlier, this is the error we got. It says lifetime may not live long enough, and then it points at the ID argument and labels its lifetime as tick1. So what's the problem? The important line is this one. Returning this value requires that tick1 must outlive tickStatic. The compiler is telling us that your async block is capturing the ID argument, which is a reference that only lives for some generic lifetime tick1. But the return type is a trait object, and by default, trait objects have a static lifetime. So our function signature is accidentally promising that the returned future can live forever, while our implementation is actually building a future that is bounded by the lifetime of the ID argument, which cannot live forever. This mismatch is why the compiler is complaining. Now, the compiler also gives us a hint at the bottom. It says, to declare that the trait object captures data from argument ID, you can add an explicit tick_lifetime bound. Tick underscore is an anonymous lifetime. When we write tick underscore, we're telling the compiler, please don't assume that this returned future has a static lifetime. Instead, infer this returned future's lifetime from the lifetime of the function arguments it captures. So let's follow the compiler's suggestion. Note that when we make changes to this function signature, we also have to update the trait definition. Okay, so we followed the compiler's suggestion, but now we see another error. Again, at the top we see, lifetime may not live long enough, but the rest of the error is different. First, the compiler labels the lifetime of the reference to self as tick2, and the lifetime of the ID argument tick1. Then it states, this method was supposed to return data with lifetime tick2, but it returned data with lifetime tick1. The problem is, the anonymous lifetime we added to the return value inferred that the lifetime of the returned value should be tied to the lifetime of self, but given our implementation, it should actually be tied to the lifetime of the ID argument. The compiler goes on to give us a suggestion. It tells us to consider introducing a named lifetime parameter. In other words, a generic lifetime annotation. Let's give that a shot. First, we'll define the generic lifetime tick_a. Then we'll assign that lifetime to self, ID, and the returned future. This tells the compiler that the returned reference cannot outlive either input, and with this in place, our code compiles. Now, even though this function signature works for our current implementation, it can be improved. Specifically, we want to make sure the lifetime constraints are as flexible as possible, so our code doesn't break when the implementation changes. So instead of defining just one lifetime, let's define 3 lifetimes and make their names more descriptive. First, we'll define tick service and assign it to self. Then we'll define tick ID and assign it to ID. And finally, we'll define tick future and assign it to the returned future. The next step is to establish a relationship between these 3 lifetimes. If you recall from our previous example, we can use a where clause with lifetime bounds to accomplish this. This code is saying that lifetime service and ID must both live at least as long as lifetime future. Or to say it another way, lifetime future is not allowed to outlive lifetime service or ID. We'll also add one more lifetime bound for self, the concrete type implementing the user service trait. Basically, this prevents us from returning a future that outlives the service value it captures data from. So now we have a more flexible function signature. The returned future can now borrow from any of the function arguments, and the function signature is general enough to support different implementations without breaking. Great! This is our final implementation of the user service trait. And this is what our user service trait looks like in the end. Now, if we had to write all this out every time we wanted to define a trait with async methods, it would be a complete nightmare. This piece of code includes some of Rust's most complex features: dynamic dispatch, futures, pinning, send and sync bounds, and multiple lifetimes. Luckily, we can tame this complexity by using an even more complex and powerful Rust feature. That's right, I'm talking about macros. Instead of writing all of this out manually, we can simply annotate our trait with an attribute macro. Async trait is actually a real macro that is provided by the async trait library. And now you know exactly how it works under the hood and why it's needed. What a journey! We went from this piece of simple code to this monstrosity, all the way back to this simple definition. Along the way, we learned about Rust's most complicated features, and hopefully, now you have a better understanding of Rust. If this video made you realize how powerful Rust is, and why it can be challenging to master this language, here's the good news. You can be part of our Rust Live Accelerator program. Today, we're officially opening applications for this private mentorship program, and applications will stay open for just a week. There are only 30 spots available, and you can click the link below to apply. Inside the Rust Live Accelerator, I work directly with developers like you who want to master Rust at a professional level, use Rust at their current workplace, or land their very first Rust job. So if you want hands-on guidance, production experience, and to kickstart your Rust career, click the link below to apply, and I'll talk to you very soon.